On this question, we want to find vertical asymptotes and create a rough sketch of the graph near each asymptote. We have the function f of x equals 6 over x minus 3. So to find vertical asymptotes, we first need to factor both the numerator and denominator. In this function, we have 6 in the numerator, which is already factored, and x minus 3, which is already factored. And the reason why we factor the numerator and denominator is because we want to look for the other type of break in the graph or discontinuity in the graph, and that is a hole. So the other type is a hole. And when there are common factors, that's when we have holes in the graph. So because we look at the numerator and denominator and there are no common factors, we know that we don't have any holes in the graph. And once we've established that there are no holes, we can take the denominator and set that equal to 0. And we find out that we have a discontinuity, and because that discontinuity is not a hole, we know that it is a vertical asymptote. So this graph will have a vertical asymptote at x equals 3. So let me draw a sketch of a graph. Let me make that a little bit smaller. And at x equals 3, we draw a vertical dashed line. And the definition of a vertical asymptote is that as x approaches that value, the y will approach infinity or y will approach negative infinity. And so we need to figure out whether we're going to be drawing that graph going towards positive infinity or negative infinity. And this is on the 3 plus side, to the right of 3. And we need to figure out whether we're going to go to infinity or negative infinity on the 3 minus sign, which is less than 3. So that's what we're trying to figure out when we want to give a rough sketch of the graph. So to do that, we're going to pick a value that is a little bit more than 3 and a value that's a little bit less than 3 so we can figure out what's going on each side. So I'm going to pick something that is less than 3, which I'm going to choose 2.9. That's something that is just a little bit less than 3. And I'll pick, for something that's a little bit more than 3, I'll pick 3.1. And we're going to plug that into our function. So f of 2.9 is 6 over 2.9 minus 3. And this denominator, 2.9 minus 3, is going to be negative. And we have positive in the numerator. Positive divided by negative is a negative. So what that tells me is that on the left side, below 3, the graph will approach negative infinity. And then I'll do the same thing. I'm going to calculate f of 3.1. That's 6 over 3.1 minus 3. That's a positive value, which is 6, over 3.1 minus 3 is also positive. Positive divided by positive is positive. So on the other side, my y is going to approach infinity. So this gives us a sketch of the graph near the asymptote x equals 3. On this question, we have the graph that is shown on the right here. And this graph is created using one horizontal shift and one vertical shift of the graph. and it's a shift of the graph of this basic function y equals x squared. And what we want to do is we want to write a function that describes the graph on the right. So it tells us that we're using one horizontal shift and one vertical shift. And we're starting with this equation here, y equals x squared. So just a reminder, that equation y equals x squared is the graph of a parabola, and the vertex of that parabola is right at the origin, 0, 0. So we're going to be able to tell where this new graph has shifted vertically and horizontally based on where the new vertex is. So if we count over, we've got 1, 2, 3, 4. We shifted to the right 4. And then down 1, 2, 3, 4, down 4. So we want our equation to represent those two shifts. Now when you have a shift in the graph, that is when you either add or subtract to your basic function. So we have two shifts in that one of them is a horizontal shift and one of them is a vertical shift. And the way you distinguish between horizontal and vertical is by adding in different locations. Now the horizontal shift affects the x, and the vertical shift affects the y. So the location of the horizontal shift is going to be inside, where it's closer to the x, and the vertical shift is going to be outside, where it's closer to the y. So if we take this equation and onto the x, we either add or subtract, this is going to create a horizontal shift. And outside of the parentheses, if we add or subtract, that's going to create a vertical shift. Now, the whole thing we need to figure out now is whether we need to add or subtract. Whenever we're moving to the right, we're going to subtract, and whenever we're moving down, we're also going to subtract. If we were moving to the left, we would add. If we were moving up, we would add. So in this one, we want to shift right 4, so we're going to subtract 4. We also want to shift down 4, so we're going to subtract 4. So we get our equation, y equals x minus 4 squared minus 4, and that is the equation of this graph shown on the right. On this question, we want to use the quadratic function f of x equals x squared plus 2x minus 12 to address the following questions. We want to find the vertex. We want to determine if the parabola opens up or down. And we want to find the axis of symmetry. So let's start with the vertex. There are two different ways for us to find the vertex when the equation is written in this general form. The two different ways involve a vertex formula or a process called completing the square. So I'm going to show you both. With the vertex formula, the vertex is usually written as an ordered pair HK, and the formula that we have for the vertex is negative b over 2a. The letters a and b refer to coefficients of the different terms in our quadratic. So when we have our quadratic, we say that it's written in ax squared plus bx plus c form. That's the general form. And a represents the coefficient on the squared term, b is the coefficient on the x term, and c is the constant. So looking at our example, our x squared term has no number as the coefficient, so we assume it to be 1. So a is 1. The coefficient of the b term is a 2, and the constant is negative 12. So we're going to work this out with the formula. Negative b is negative 2 over 2 times a, which is 1. Negative 2 over 2 is negative 1. And then we're going to find the y part of our vertex, k, by substituting into our function. So we're going to take that negative 2 and substitute it into the function to get the y part. So that's f of negative 1 is negative 1 squared plus 2 times negative 1 minus 12. Negative 1 squared is 1 minus 2 minus 12. 1 minus 2 is negative 1, and 1 minus 12 is negative 13. So we have the vertex of our quadratic function, our parabola, being negative 1, negative 13. So that's one way to find the vertex, using the vertex formula. Let's try the other way, which is using completing the square. So when we complete the square, we start with our function, f of x equals x squared plus 2x minus 12. And this function, this quadratic function, is in general form. What we're going to do is try to rewrite it in the vertex form, which is a times x minus h squared plus k. And when we write it in that vertex form, it's very easy to recognize what the h and the k are, and that is our vertex. So with this completing the square process, you first want to group these x terms together and factor out the coefficient on the x squared term. On this example, because x squared doesn't have a coefficient, we don't have to factor anything out. So we're just grouping it together. Then I'm going to make a little bit of room inside this grouping for what I call the magic number, and this magic number is going to complete the square. So let me do the work on the side. You're going to start with the coefficient on the x term, 2. You divide that by 2 and then square it. 2 divided by 2 is 1, and 1 squared is 1. So our magic number for this example is 1. And we want to write that magic number inside the parentheses. But you're not allowed to just write any number you want. You have to keep an equation that is balanced. So whatever I change in the equation, I have to balance it out by doing the opposite. So I wrote a 1 inside the parentheses. There's a 1 outside the parentheses. So if I multiply those two together, 1 times 1 is 1. So by writing a 1, I've added a 1 to this equation. To balance that out, I need to subtract 1. So now I'm ready to factor what's in the parentheses. In the parentheses, this factors to be x and x. 1 times 1 is 1. Positive 1 plus positive 1 will give me a positive 2 in the middle. And then negative 12 minus 1 is negative 13. The x plus 1 times x plus 1 becomes x plus 1 squared. And we've now written this equation in the vertex form. You can recognize the h and the k from the equation, and we get a vertex of negative 1, negative 13, which is the same vertex we got with the other method. So either one is acceptable to find the vertex. So let's move on to the other parts of this problem, part B. Does the parabola open up or down? And to determine that, we want to focus in on the coefficient of our squared term, a. And whenever a is positive or greater than 0, we know that the parabola will open up. And when a is less than 0, it will open down. So in our example, we have a coefficient of 1 on our x squared term and a coefficient of 1 even when it's written in the vertex form. That's positive, so that means that this parabola opens up. And then finally, the last question is axis of symmetry. Every parabola is going to be symmetric around its vertex. So if we just sketch a graph of a parabola, its vertex is here. And if we draw a vertical line going through that vertex, you can see that we have a mirror image on either side of that vertical line. So we call that line the axis of symmetry. So it's a vertical line. The equation of a vertical line is always x equals a number. And because our vertical line is passing through the vertex, we can use the x coordinate of our vertex to create that axis of symmetry. So x equals -1 is the axis of symmetry. For the given rational function, answer parts A through C. We're given this function f of x equals x squared plus x minus 56 over x squared plus 7x. And with this rational function, we want to determine the domain. We want to determine the y-intercept, if any, and determine the x-intercepts, if any. So let's start with the domain. When we have a rational function, we have variables in the denominator. And if there is a 0 in the denominator, we have that division being undefined. Division by 0 is undefined. So that's our concern when we find the domain. We take the denominator, which is x squared plus 7x. We set that equal to 0, and we're going to solve. This can be factored. I'll factor out an x. If I factor out an x, I'll have x times x plus 7. And I can set each factor equal to 0. That gives me x equals 0 and x equals -7. These two values are going to be the restricted values. They cause the denominator to equal 0, and division by 0 is undefined. So we need to exclude these values from the domain. So we're excluding -7 and 0 from the domain, but all other real numbers will be included in the domain. So we're going to write this in interval notation. We want to represent each one of these shaded regions with a lower bound and an upper bound. So for the first one, that line goes on forever, so we use -infinity. That shaded region stops at -7. The next shaded region starts at -7 and goes to 0. And the next shaded region starts at 0 and goes to infinity. So we have the domain of this rational function being -infinity to -7, union with -7 to 0, union with 0 to infinity. Let's move on and talk about finding a y-intercept. You find a y-intercept by letting x equal 0. So that means I'm going to substitute a 0 into the function. Now keep in mind over here we already said that 0 is a restricted value. So we're going to see that this isn't going to work out. We have 0 squared plus 0 minus 56 over 0 squared plus 7 times 0. This gives -56 over 0. We said division by 0 is undefined, and that means that we don't have a y-intercept for this rational function. So then let's take a look at the last part, finding any x-intercepts. When you look for an x-intercept, you let y equal 0. Now we're using function notation in this example, so instead of writing y, we write f of x. So we want to set our function f of x equal to 0. We have 0 equals x squared plus x minus 56 over x squared plus 7x. To solve this, we would multiply both sides by the denominator, x squared plus 7x. And this is going to clear the fractions. So we have that denominator canceling out, and then on the left-hand side, 0 times x squared plus x is 0. So in order to find the x-intercepts, we need to solve this quadratic equation, 0 equals x squared plus x minus 56. I believe I can factor this quadratic, but if you can't factor it, you can always fall back on the quadratic formula. So x times x is x squared, and for 56, 7 times 8 is 56. I'm going to use a plus on the 8 and a minus on the 7. We can use the zero product property and set each factor equal to 0. We have x minus 7 equals 0 and x plus 8 equals 0. I'm going to add 7 to both sides to get x equals 7. Subtract 8 to get x equals negative 8. And we do have x-intercepts here at 7, 0 and negative 8, 0. You might want to check while you do this with your restricted values to make sure that the x-intercepts you came up with aren't one of those restricted values. In this case, they are not, so they are the x-intercepts for this rational function. Use the quadratic function f of x equals 2x squared plus 4x minus 7 to address the following. We want to find x-intercepts and y-intercepts. Now part A is intercepts, but I'm going to start with y-intercepts because they're always a little bit easier. So when you're looking for a y-intercept, you're going to let x equal 0. I'm going to substitute a 0 into the function, and that gives 2 times 0 squared plus 4 times 0 minus 7. This gives 0 plus 0 minus 7, and that's negative 7. So the ordered pair, 0, negative 7, is the y-intercept. Then let's take care of x-intercepts. When you're looking for an x-intercept, you're going to let y equal 0. In this example, we're using function notation. So f of x is y. We're going to set f of x equals 0. So we create the equation 0 equals 2x squared plus 4x minus 7. We want to solve this quadratic equation. I'm going to try to solve it by factoring first, but if that doesn't work, I can always use the quadratic formula. So let's see if this factors. So this first term is a 2x squared, so I'll use 2x and x for the first terms. This last term is a negative 7. The only factors of negative 7 are 1 and 7. So I'll use a 1 and a 7 just to try it out. And the inside gives me 1x and the outside gives me 14x. And when I add those together or subtract those, it doesn't give me the right number in the middle. I need a 4x in the middle. So this is not going to work. So let me try putting the 7 here and the 1 here. So let's put the 7 and the 1 like this and give it another try. When I multiply the inside, that would give me 7x, and the outside 2x. And when I look at these two numbers, 7 and 2, and I add them or subtract them, 7 minus 2 is 5, 7 plus 2 is 9. Neither one of them give me the right number in the middle. Now I've exhausted all the possibilities of this one. There weren't very many on this one because the factors of 2 are only 2 and 1, and the factors of 7 are only 7 and 1. And so I've gone through all of those possibilities, and none of them work to factor this quadratic expression. So I am going to have to fall back on the quadratic formula to solve this. So let's take a look at that quadratic formula. So the quadratic formula deals with an equation, a quadratic equation in this format, ax squared plus bx plus c. And we can solve this quadratic equation using the formula x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So we are going to use the coefficients of a, b, and c, 2, 4, and negative 7, and substitute them into this formula. So if I substitute those values in, I'll have x equals negative b. b is the coefficient of the x term, so that's negative 4, plus or minus the square root of 4 squared, minus 4 times a, which is 2, times c, which is negative 7, all over 2a, which is 2. So I've substituted the values of a, b, and c into the formula, and I want to simplify the formula using order of operations. So inside the radical, we have 4 squared, which is 16, 4 times 2, which is 8, 8 times 7 is 56, and we have 2 negatives multiplied and 1 positive. 2 negatives multiplied create a positive. In the denominator, 2 times 2 is 4. Inside the radical still, we need to do that addition to get 72. 16 plus 56 is 72. And then I want to reduce this radical or simplify that radical. So when I simplify, I'm looking for factors of 72 that have a perfect square. So I know that 72 is 36 times 2, and 36 is a perfect square. So that's the one I'm going to use. 36 times 2 over 4. The square root of 36 is 6. The 2 will stay inside the radical because it's not a perfect square. And then I'm going to look for a common factor among these three terms. All three of them are even, so I can divide a 2 into each one of them. So that's negative 2 plus or minus 3 square root of 2 over 2. So these will be the solutions to the equation and also the x-intercepts. So we have two x-intercepts, negative 2 plus or minus 3 square root of 2 over 2, comma 0 are our x-intercepts. Write an equation for the inverse function and then state the domain and range of f and f inverse. In this question, we have the function f of x equals x cubed plus 4. The first thing I want to do is find the inverse function, which we call f inverse. So to find that inverse function, I'm going to change f of x to y. And then I'll switch the x and the y And I'm switching the x and the y because that is what inverse functions mean. The x and the y are switched in these type of equations. So that's basically by definition because we're looking for an inverse function. And then I'm going to solve for y in this new equation. So I want to isolate the y. So to isolate the y, I'll subtract 4 on both sides. And I need to get rid of that cube, and the opposite of cubing is cube rooting. So I'm going to cube root the left and cube root the right. The cube root and the cube cancel each other out, giving me y. And then on the left, I have my inverse function, cube root of x minus 4. So we can label that as f inverse. F inverse is the cube root of x minus 4. The next thing that we want to do is find the domain and range of f and f inverse. Now we have some strategies for finding the domain of different types of functions. So I'm going to find the domain of each of these f and f inverse first. So if I look at f of x, that is x cubed plus 4. This type of function is called a polynomial function. And with polynomial functions, there are no restrictions on the domain, meaning that no matter what real number we substitute in, we are going to have a defined y value. And so because of that, we can say that the domain of f is all real numbers, negative infinity to infinity. We'll do the same thing for f inverse. We just found that f inverse is the cube root of x minus 4. As I look at this function, I would categorize this as a root function. We call it a root function because of the radical. Now with root functions, you want to pay attention to the index. This has an index of 3. And the reason why you want to pay attention to the index is because root functions with an even index have restrictions on the domain, but root functions with an odd index have no restrictions. So we have an index that is odd, so there will be no restrictions on the domain of this function. The domain of f inverse is also all real numbers are negative infinity to infinity. Now we also want to find the range of f and f inverse. Now we don't have as many strategies for finding the range like we did the domain. But if you'll remember, what we did earlier is we switched the x and the y. So what we know about inverses is that the x and the y switch, domain are the x's, range are the y's. So if we switch the x and the y, the domain and range also get switched. So what that means is that I can use the domain of f inverse as the range of f. And I can use the domain of f as the range of f inverse. So we now know that the range of f is all real numbers, negative infinity to infinity, and the range of f inverse is all real numbers, negative infinity to infinity. For this function, f of x equals 1/2 x plus 2. It is 1 to 1. And what that means is that if the y's are different, the x's will be different as well. Or I guess the opposite of that. If the x's are different, the y's will be different. Then what we want to do is find the inverse of our function f. We want to state the domain and range of f and state the domain and range of f inverse. So let's start by finding the inverse. When we're looking for the inverse, I'm going to start with my function f of x equals 1/2 x plus 2. And I'm going to change that f of x to y, just to make the equation a little simpler to write and there are fewer symbols there. Now with inverse functions, the x and y values get switched. So in the equation, I'm going to switch the x and y values. And then I'm going to solve for this y, and that will give me the equation of my inverse function. So I'm going to subtract 2 to get x minus 2 equals 1/2 y. And multiplying by 1/2, I want to get rid of that. So I'm going to multiply by the reciprocal 2 over 1. So I multiply by 2 over 1 on the right and multiply by 2 over 1 on the left. So on the right, all of those fractions cancel, leaving me with y. And on the left, I'm going to treat that 2 over 1 as 2 and use the distributive property. That will give me 2x minus 4. So I now have my inverse function, which I'm going to label as f inverse, and it is 2x minus 4. So now that I've found the inverse function, I want to state the domain and range of f. My function f is 1/2 x plus 2. This is a linear function. And a linear function is a type of polynomial function. And polynomial functions have a domain of all real numbers, -infinity to infinity. Then for my inverse, I have the equation 2x minus 4. And this is also a linear equation, linear function, which is a type of polynomial. So its domain is all real numbers, -infinity to infinity. With inverse functions, as we saw here, the x and the y value get switched. The domain are the x's, the range are the y's. And so when the domain and range get switched, the x and the y get switched, the domain and the range get switched. So I can use the domain of the inverse function to find the range of the original function. So our function f has a range of all real numbers. We can do the same thing with the inverse. So we have the range of the inverse also being all real numbers, -infinity to infinity. For this question, what we want to know is the function with the graph on the right 1 to 1. So we're given this picture and we want to know if this function represents a 1 to 1 function. So I have here the definition of 1 to 1. A function f is 1 to 1 if for any values a not equal to b in the domain of f, f of a is not equal to f of b. So what this definition is saying is that if the x values are different, the y values will be different if you have a 1 to 1 function. Whenever we're looking to determine if a graph represents a 1 to 1 function, we use something called the horizontal line test. And with the horizontal line test, If every horizontal line intersects the graph in at most one place, then we can say that that function is a one-to-one function. So what we're going to do is we're going to draw horizontal lines all over the graph and record how many times that horizontal line intersects the graph. And so we can see that we have this first horizontal line intersecting the graph in only one place. The second horizontal line intersects in only one place. But we do have some horizontal lines that intersect the graph in more than one place. And that's violating the definition of one-to-one. So for a one-to-one function, we need different x values to have different y values. So let's take, for example, this horizontal line right here. With this horizontal line, it's hard to see with all of the vertical lines, but this ordered pair here would have an x value of -2. And this ordered pair here has an x value of about 2 and a little bit more. Let's just say 2 as an estimate. So these two ordered pairs on the graph have different x values. -2 is not equal to +2. However, when we look at their y values, because they're on this horizontal line together, they do have the same y values. F of -2 is equal to f of 2. But for it to be one-to-one, we needed them to be different from each other. So this violates the definition of one-to-one, and we're going to say no, that this graph is not a one-to-one function. The graph of a function f is given. Use the horizontal line test to determine whether f is one-to-one. So we're given this graph here on the right, and we want to know if this graph is a one-to-one function using the horizontal line test. Before we do that, let's just state the definition of a one-to-one function. A function f is one-to-one if for any values a not equal to b in the domain of f, f of a is not equal to f of b. So this definition says that if the x's are different, the y's should be different. And if that's true, then we have a one-to-one function. So one-to-one function will have different x's having different y's. And we use the horizontal line test to determine whether a graph represents a one-to-one function. And this horizontal line test says if every horizontal line intersects the graph of a function f at most once, then f of x is one-to-one. So let's pause for a second and talk about why we use a horizontal line for this situation. With a horizontal line, if you think about the ordered pairs on a horizontal line, those ordered pairs will have x's that are different from each other. So I'm going to write x1 and x2. However, the y values are the same. And so when we're looking at a horizontal line violates the definition of a one-to-one function. So we use it as a comparison, and if we see that horizontal line crossing more than once, we know that function is violating the definition of one-to-one. So we're looking for our horizontal lines to cross at most once so that we can call it one-to-one. If it crosses more than once, we know it's not one-to-one. So we're going to draw horizontal lines on this graph. And as we draw horizontal lines, we're going to pay attention to how many times the graph crosses the horizontal line. So we can see that every one of the horizontal lines is only crossing in one place. And I know it's a little bit hard to tell at the end here, but this end of the graph is consistently moving to the right and up, and so it will never repeat those y values. So because every horizontal line is crossing at most once, then we can say that this function is a one-to-one function. So is this graph a function? Yes, it is a is it a one-to-one function? Yes. In this question, we're given f of x to equal -5 over x plus 1, and g of x equals square root of x plus 21. We want to find f composed with g of -5. There are a couple ways we can go about this. One way to go about this is to build or construct the function f composed with g, and then once we've built that function, then substitute the -5 into that function. So let's start with that way, and then I'll show you another way after that. So if we want to find f composed with g of x, we need to know what the operation of composition actually means. This operation of composition means to substitute one function inside of another function. And the way that we write it is that the outside function is the one that's written to the left of the composition symbol, and the inside function is the one that's written to the right of the composition symbol. So I'm going to be substituting g of x into f of x. So to do that, I'm going to take this function g of x, and it's going to get substituted into f of x, and it gets substituted in for this x and any x that might be in the equation of f. So that would give us the equation -5 over square root of x plus 21 plus 1. So this is the function f composed with g, -5 over square root of x plus 21 plus 1. Now that we have built or constructed that function, I'm going to be able to substitute a -5 into the function. That would give me -5 over the square root of -5 plus 21 plus 1. -5 plus 21 is 16. Square root of 16 is 4. 4 plus 1 is 5, and -5 over 5 is -1. So we were able to calculate f composed with g of -5 to be -1. But now I'll talk about the other way you might be able to find f composed with g of -5. So I'm going to start with f composed with g of -5. And once again, I want to keep in mind what this operation of composition means. It means substituting one function inside of another function. So that means that I can write this as f of g of -5. G of -5 means to substitute -5 into the function called g. So into this function, g of x, I'm going to substitute a -5. So that's square root of -5 plus 21. And -5 plus 21 is 16. And the square root of 16 is 4. And now that I've worked out that inside part, worked out the inside, I can now work out f of 4. f of 4 means to substitute a 4 into the function called f. So when we do that, we would have negative 5 over 4 plus 1. Negative 5 over 5 is a negative 1. So we've got the same answer that we worked out in a different way. Thank you for checking out my videos. Have a great day.